Our next assumption, the relationship between the dv and the variate, or the combination of all the IVs, is intrinsically linear and additive. This gets us to our assumption of linearity. Now, I want to be careful here. The key word is intrinsically linear and additive. Because look, it doesn't mean perfectly linear in all respects. We already know, we talked about moderation, we talked about how we can actually model curvilinear relationships. And our interaction term, right, that's not additive, that's multiplicative. So we know in an absolute sense, where that's not what we're talking about here. We're talking about intrinsically linear and additive. And what does that mean? It means that every expected value of y has to be linearly related to all other expected values of y. So let's talk about what that means, right? So in our basic bivariate, and this is where this comes most to play, in our bivariate correlation, right, we get x, we have y, and we have some scatter plot. And OLS regression gives us the line of best fit within that scatter plot that describes the relationship between x and y. These then are the expected values of y. Now remember, there's prediction error, so they're not the actual value of y, they're the expected value of y given x. These are all linear related to each other because this is a line, right? So that's fairly obvious. This is the most obvious in the bivariate relationship. Now, if this line, or if this relationship instead looked like this, and some U shape or something like that, and the line of best fit looks something like that, well, that's not a line, right? The line is actually, the OLS regression for this is something like that. This is breaking assumptions. And what we are suggesting here is that there is some third variable that describes this relationship. So if we want to get to a linear description, we need a third variable here. Well, we've done that already when we talked about moderation. The third variable in this case is x, right? And so x times x then describes that relationship. So it turns out that what all this means, if we don't have a perfectly linear thing on a scatter plot, a bivariate scatter plot, that means there's something else going on that we need to add in there. What's important is that the y hats, the expected values of y, are all related to each other in a linear fashion, intrinsically linear and additive. Now, if we add to this a second variable, right, then that comes, say z, right, that actually comes out this way. And unfortunately, I can't draw a 3D scatter plot, but it would look something like a football. And across that football, there is a plane, right? So we put a piece of paper that cuts that football. All the expected values of y need to be on that plane. We call that the plane of best fit. And as we add additional numbers, it becomes just called, a more general way, the surface of best fit. That surface of best fit, all expected values of y have to be on it, and has to describe a linear and additive relationship. Okay, this can get a little confusing. And really, where this assumption comes into play is the question of how do we break this assumption? How do we know we've broken it? So, a couple ways. Number one, when y, the dv, is not continuous. If the dv is not continuous, then we're not going to get a linear and additive model, right? So, for instance, if we were to model wins and losses, right, and our outcome was to try and predict wins or losses, that's not linear, right? That's either you win or you lose. It's not continuous. And so having a categorical y or having some non-continuous y, even an ordinal y, suggests that there's an issue going on there. The other way is to have an unspecified moderator variable, right? So in this case, we have an unspecified moderator variable. In this case, it's x times itself. X is as a first variable and also as a second variable, second variable and a third variable, with y being the first variable. So having some moderator variable is also a way that this can be a problem. So when a moderator variable exists, but we don't include it in the model, we're breaking the assumption of linearity. That's another example. Or again, when y is not continuous, we're breaking the assumption of linearity. And then the other thing is when the prediction error term depends on the level of more than one predictor. And this is probably the key place where we start to really have a problem. Right? So remember when I talked about measurement error, that non-random measurement error comes into play when the amount of error involved depends on the variable that you're measuring. Well, the same thing can happen in prediction error. If the amount of prediction error is non-random, if it's related to what the measure of y is, if it's related to the value of y, and if the prediction error changes depending on the value of y, then you don't have a linear relationship among all the expected values of y, and that's going to be a problem. So the big three ways to remember that we can break the assumption of linearity is if there's an unspecified variable that we have not properly included, if y is not continuous, or if our errors of prediction are dependent on the value of y.